All right, everyone. So now we are going to talk about, if there's one thing I want you to leave this class with, it's this information: how to interpret a stress strain curve. Whatever type of engineering discipline that you're in, you're going to have to be able to interpret this curve. So what we're plotting here is essentially stress on our y-axis, strain on our x-axis, effectively, and we're looking at the evolution of stress versus strain until a material fractures. So you can see three distinct regions, and they're all very different in terms of how the material behaves. So stage one is elastic deformation. It is linear. If you're doing uniaxial, basically simple uniaxial loading, the elastic region is linear in the relationship of stress and strain, and this is where stress is equal to this and this. Only time we're going to be using this. Elastic deformation means that atomistically you are pulling on the bonds, but you're not breaking the bonds. There are dislocations in your material, as we discussed in lecture 2, and defects, but you are not initiating any dislocation or defect motion. So you're just pulling on the bonds. Additionally, when you release the load in this region, the material will pop back into place. So there's no permanent plastic deformation. Plastic deformation, as you see here, is permanent deformation. So when I release the load, my material is permanently changed. So here I am initiating dislocation motion. I am pulling on the bonds, I am breaking bonds potentially, and dislocations are becoming mobile. So you see here you lose the linearity here, and then you're now nonlinear, and other things can happen here. So you can see this is our yield strength, sigma y. You could also have your ultimate tensile strength is just the highest yield strength, or the highest stress value in your material. So we'll be talking soon about basically strain hardening, strain softening, or perfect plastic deformation. But in this plastic regime, there is no relationship or constitutive relationship between stress and strain. We're going to be, in this class, calculating stresses and strains. That only holds for stage 1 here. Stage 2 is a completely empirical field. There are some relationships that you can kind of intuit empirically. There are some equations that tell you scaling, but there is no first principles equation that tells me when I apply a stress, this is my resulting strain. And finally, stage 3, fracture. Everyone wants to see fracture, but again, it's kind of quite boring. It is going to be a competition between the surface area that you create versus your elastic strain energy released, or basically relieved in essentially the bonds. So that's when fracture happens. And then there's, again, stochastic. There are some basically first principles relationships that try to intuit that, but it's also a very highly empirical field as well, and it's stochastic. So it depends a lot on the heterogeneities in their material. You can also see your yield stress, your yield strain, your strain at failure. This is your stress at failure as well. So these are kind of the common components that you see. The area under this curve, under the whole area, that will yield you your toughness. Now, if I integrate this curve, so this is stress. So if I integrate the curve, I'm going to be left with a value of a Newton per meter squared, or Pascal. So my toughness can be represented in Pascal, but if I multiply out by the volume, so times meters cubed, then that gives me Newton per meter. That's a joule. So really the toughness is all about how much energy can the material absorb prior to fracture. And you have elastic strain energy here if you just integrate that particular section. So we kind of talked about this already. So elastic regime, again, linear, it's reversible, no hysteresis, pop back upon loading. Again, bonds are being pulled, not broken, no dislocation motion. There are dislocations, there are defects, but again, no permanent plastic deformation. They pop back. Pulling on the bonds, not breaking any, again, et cetera, et cetera, et cetera. Most materials will behave linearly at strain smaller than 0.002. That's a good value to kind of remember. Some of these values that we're going to kind of talk about here are good to remember. So most materials will behave linear and elastically. Again, some materials are isotropic, so they behave the same in all directions. Some are going to be anisotropic, so the properties are going to be varying. So titanium, composites, wood, polycrystalline metals will typically behave isotropically. And again, we can kind of see some of the values here. So what are some critical values in this linear or stage 1, the elastic regime? Young's modulus. Young's modulus is the value. If we say a material is stiff, I'm referring to the Young's modulus. So if it's stiff, I have a high Young's modulus. If it is described as compliant, that is a low Young's modulus. So you see diamond has a very high, gigapascal. Young's modulus, alumina. These are all kind of ceramic materials, except for diamond. So around 300 gigapascals. Metals, you're going to be looking at hundreds of gigapascals, 69 gigapascals, and then polymers are going to be a little bit less. They can vary quite a bit, as you can see, from 0.01 to, I'd say, could get to about 10 GPa. So quite a large variety, and orders of magnitude shift. Actually, you can see it's 1, 2, 3 orders of magnitude, at least 3 orders of magnitude, shifting in your Young's modulus value. So definitely, polymers are typically more compliant materials. So these are typical values you can kind of just memorize and use as rule of thumbs when you're working with these systems. So ceramic, you could say it's about 300 gigapascals, metal 100, polymer, just say about a gigapascal. Excellent. Plastic regime, again, we talked about before, plastically, it's irreversible. Again, there will be hysteresis upon loading and unloading it. Again, motion, stretching, breaking of bronze, moving those values. What are some of the key parameters? Yield stress. Yield stress, you could hear that referred to as strength, although again, it's not specific, so we don't want to call that. Yield strain, again, a very specific value. In industry, you'll typically see that, okay, well, the way that they calculate the yield stress is this 0.02 offset method. So you use the same slope as the Young's modulus. You start it at 0.02, and then you see where the line intersects, and that's going to be your yield stress value. I have personal issues with this, but because, I mean, again, you can do visual check, you can use some, statistical methods. So I don't like this technique, but you should know essentially how to do it just in case you're asked to do it as well. So again, it's basically saying if I want to measure these, basically where is the yield stress occurring, I'm going to take the same slope and of here, I'm going to offset it by 0.02. I'm going to do the same slope, and I'm going to see where it crosses, and that's going to be my yield stress value. I really don't like this method, but you'll see that a lot in industry. Ultimate tensile strength, very clear to see, highest value. That is typically where the necking is going to occur. So necking is basically a deformation mechanism where when you start to plastically deform it, and especially once you hit the ultimate tensile strength, it will thin at some region. So you decrease the cross-sectional area locally. There's instabilities, heterogeneities. Typically, that's where it occurs. You could also see strain hardening occur because, again, remember, stress is equal to force over cross-sectional area. In the neck, my force is still the same that's being applied, but that cross-sectional area is decreasing, so you would actually, if it was the true stress, you'd see a jump in there or an increase. But because our initial area is greater than our true cross-sectional area in the neck, you actually will see basically a dip compared to what it should be. More on that a little bit later when we have some cool little things to look at. So ultimate tensile strength is also referred to as strength as well. So we have to be careful of kind of that notation, and that language is very, very, very important. And finally, fracture. So fracture, loud pop, everyone's scared. Fracture stress is going to be our sigma F, fracture strain here. Fracture strain is also referred to as ductility. So the higher the value, more ductile, lower the value, brittle. So again, when do we bond? When are we going to actually break? Well, when we don't want to create surfaces, but when the energy penalty to create surfaces is less than relieving the elastic strain energy, then we are going to fracture. I know we're getting a little bit ahead of ourselves, but that's what we'll see soon. And again, very similar to plastic regime, it is empirical, stochastic, depends on those local inheterogeneities, and that's what we'll be looking at there. A couple other material properties. Again, elastic strain energy, we kind of mentioned it previously. It's going to be in that elastic regime, taking the basically area under the curve, and you could calculate that. There's a couple other ways you can do it. So if we take an RVE, representative volume element, I think we'll see it over here. So this is our RVE. We could actually calculate the elastic strain energy here. So if I take my RVE, representative volume element, here's my coordinate system, 1, 2, 3, and I'm going to apply, let's say I'm applying a stress in this direction. The force is just going to be my sigma 1,1 times my, say this is delta 1. Actually, that would be delta 2. This would be delta 1, and this would be delta 3. So the force is just going to be, again, stress is going to be equal to force over cross-sectional area. So the force is going to be the stress times this cross-sectional area right here. Again, assuming initial force 0, our average force would be this. If you look at the deformation, so the change in that delta 1 direction, remember our strain 1,1 is the change over my initial direction. So I could look at the displacement here, and we know work. How do we define work? Work is a force times some displacement delta x. So we have our force average. We have our value right here. So this would be your work. If you divide out by the volume, this is equal to our volume, and we find this value here. Now we can also we can actually calculate this simply by doing what looking at what we did previously. You could just take the integral. It's a little bit much easier of a method than kind of going through that thought experiment. But I know that my stress in 1,1 is equal to E times sigma 1,1. If I look at taking the integral, let's just keep it indefinite at this point. Integral of sigma 1,1 times d E11 equals the integral of E11 d E11. What is that going to be? E11 squared over 2. Substitute back in that this would be equal to basically E11 is equal to sigma 1,1 over E, and so E squared. So it would be sigma 1,1. Basically, what are we going to do? We're going to do sigma 1,1. Actually, it's going to be a second. Sorry, I'm just sigma 1,1 squared times E over E squared times 2, which would just be this gets killed out, this gets killed out, and then sigma 1,1 squared, I can rationalize that as, so sigma 1,1 times E11, because that will be sigma 1,1, it's just E over 2. So we could actually look on that one. And we can see that this right here, oops, sorry here, this is equivalent to right here. So again, you could kind of convince yourself of that if you just plug in E11. So if we plug in E11 here, it's just going to be that. So we get the same value that we're left with. So excellent. So you could do the exact same idea for shear stress as well. We haven't really talked about shear stress a little bit, but the same relationship holds. And then you could do the exact same thing for toughness. Again, energy per volume. Again, Kevlar is better than steel because again, you can extend so much more ductile for polymers than for ceramics or other materials as well. So next time we're going to talk about language and look at some example stress strain curves. So see you then. Thanks.